Okay, students, so I'm sharing. Okay, so I think now my screen is visible to you. So,
Good morning, sir.
Yeah, good morning. So we are starting with the joint distributions in the introduction to probability. Slides already I have shared as you have requested. Some students have requested. So let me start with an example. A committee of 3 is to be selected from a pool of 10 teachers consisting of 3 professors, 3 associate professors, and 4 assistant professors. Let random variable x denotes the number of professors in the committee, y denotes number of associate professor in committee, selected, number of professors, number of associate professors selected. Okay, so the x can take values because maximum of 3 can be selected. So 3 professors are there. So 0, 1, 2, 3. And similarly, y can take values 0, 1, 2, 3 because maximum of 3 associate professors can be there. So 0, 1, 2, 3. So but x comma y can take value I comma j such that I is 0, 1, 2, 3. J is also 0, 1, 2, 3 such that I plus j is less than equal to 3. This should also be satisfied. Okay. So what is the joint two-dimensional random variable has the joint PMF, probability mass function, as Pi comma j, which is probability x is equal to I, y is equal to j. So out of 3 professors, I can be selected, and out of 3 associate professors, j are selected, and remaining out of remaining assistant professor, out of 4 assistant professors, remaining 3 minus I minus j are selected, divided by 10 C3. Out of 10, we are selecting because 4 plus 3 plus 3, out of 10, 3 are selected. Okay, and such that I plus j is less than equal to 3, and I and j take the value 0, 1, 2, 3. So this is the joint probability mass function. Now you can just plug in the value of x and y, I and j value. Okay, then also you can write down x is equal to x, y is equal to y. So x is taking value, let us say 0, 1, 2, and y is taking value 0, 1, 2. Okay, then when 0, 0, then 3c0, 3c0, 4c3, because out of the assistant professor 3 are selected, 4c3 divided by 10c3. So that is coming out to be 2 by 15. Similarly, p, if we take I as 1 and j as 0, then this is 1 by 15. This is 1 by 15. Okay, so actually this is okay. So okay, sorry. So this is basically we take this value as, let me take I and j only. Okay, that will be better. So let me take because this can I can take value 0, 1, 2, 3, 0, 1, 2, 3, and j can take value 0, 1, 2, 3. Okay, so now when I is 0, j is 0, then this is 3c0, 3c0, 4c3 divided by 10c3. So that will be 4c3 upon 10c3, 4 by 120. Okay, similarly, this will be 18 by 120. And this is 12 by 120 and 1 by 120. Similarly, when x is 0, y is 1, then this is 18 by 120. Just plug in the value 36 by 120, 9 by 120. And similarly, when x is 3, y is 1, then this is 0 because a total number of becomes more than 3. Similarly, this will be 12 by 120, 9 by 120, and 0, 0. And this is 1 by 120, 0, 0, 0. So why 0, 0, 0? Because these values are coming to be more than 3. Okay, that is not possible. So in this fashion, you can find out the values. So now, if I want to find what is the probability, yes, what is the probability x is equal to 0? Then using theorem of total probability, you can just write down this is summation over j, probability x is equal to I, y is equal to j. Okay, that means sum this probability, you will get probability x is equal to 0. So that will be 35 by 120. Similarly, probability x is equal to 1. This is 63 by 120. This is 21 by 120. This is probability x is equal to 3. This is 1 by 120. Similarly, if you want to find out what is probability y is equal to 0, so you again use the theorem of total probability, summation over I, probability x is equal to I, comma y is equal to j. So sum over these values. So you will get 35 by 120. This is 63 by 120. This is probability x is equal to y is equal to 1. 21 by 120 and 1 by 120. So this is, so you can just write down this is pyy, pyj. This is probability y is equal to j, j is 0. This is probability y is equal to 0. And this you can write down probability x is equal to x. which is probability x is equal to I. So these are known as the marginal distributions. What is the probability x is equal to x? This is marginal probability mass function of x. Corresponding to 0, value is 35 by 120. Corresponding to 1, value is 63 by 120. Corresponding to 2, value is 21 by 120. Corresponding to 3, value is 1 divided by 120. So this is the marginal probability mass function of x. Okay, so this value is corresponding to 0, 1, 2, 3. This is the marginal probability mass function of random variable x. So x is equal to I and corresponding pxi. So 0, 1, 2, 3. So this is 35 by 120, 63 by 120, 21 by 120, 1 divided by 120. So in this fashion, you can find out the marginal PMF of x, and similarly you can find out the marginal PMF of y also. Now once marginals are, you have find it out, you can find out the conditional distribution also. Conditional probability mass function of x given y is equal to 1. Let me say I want to find out this. So that means probability x given y is equal to 1 x. So this will be p x comma 1 upon p y 1, where x is varying from 0, 1 to 3. So for example, I want to find out what is p x given y is equal to 1, 0. So this will be p 0, 1 upon p y 1. So p01 is, so x is 0, y is 1. So this is 18 by 120. So 18 by 120 upon py1. So that means the marginal corresponding to y at point 1, 63 by 120. So this will be 63 by 120. So therefore this is 18 by 63. In this fashion, you can find out all the values corresponding to x. What is px given y is equal to 1, x 0, 1, 2, 3. So this is 18 by 63. Then next is coming out to be 36 by 63, 9 by 63. And this is 0. Just plugging in the value, choosing the corresponding value of x and y. Okay. Total is 1 here. So if you find out the mean corresponding to this, so this will be nothing but multiplying summation x into y is equal to 1x. So multiplying this, so 1 into 36 by 63 plus 2 into 9 by 63. Okay. So in this fashion, you can find out this value also. Similarly, you can find out the mean and variance corresponding to x also and y also from here. Okay, so this was about the. So any question here? So corresponding to x and y, let us say x and y are discrete random variables. X comma y is a two-dimensional discrete random variable having joint probability mass function pxy. Then pxy is greater than equal to 0 for all xy, and the summation of pxy should be 1. Marginal density of x is summing over the joint over y, and marginal density of y summing the joint over x. Same thing we are doing. Using the theorem of total probability. Same thing we are doing. Summing over j, if I want to find probability x is equal to I, then this is summing over j probability x is equal to I, comma y is equal to j. Then what is the conditional density of x given y is equal to y? This is the joint over marginal of y. Similarly, conditional density of y given x is equal to x is joint over marginal of x. For example, as the previous example, we take a rover, a small vehicle that can move over rough grounds often used on the surface of other planets, is checked for tire wear. Headlights is checked for proper adjustment. X the number of defective tires. Y be the number of headlights that needs adjustment. Then x comma y have joint probability mass function. Let us say given by this. Okay. Then marginal density of x. You will sum this value. You will get probability x is equal to 0. This is 7 by 15. Sum over this. You will get 4 by 15. Sum here. You will get 4 by 15. So this is the marginal density of x. Now you can find out the marginal density of y also. So we will sum over these values. 4 by 15 corresponding to y is equal to 0. Then sum over these values. 6 by 15 corresponding to 1. And then 5 by 15 corresponding to 2. Okay. So in this fashion, you can also find out the conditional density of x given y is equal to 2 also. So this will be P, for example, this value, first value will be P 0, 2, Py2. So P 0, 2 is P 0, 2 is 2 by 15. This is 2 by 15 upon Py2. Py2 is 5 by 15. This is 2 by 15. In the same fashion, you will get corresponding to x 1 by 5, corresponding to 2 by 5. Now you can find out the mean and variance of x and y, and conditional mean also you can find out. So if you have to find out expected value of xy, if you have to find out expected value of x, you will use this one, summation x px. Okay, in the similarly expected value of y will be summation y py. And if you want to find expected value of xy, you will double summation xy pxy. That means you multiply 0, 0 into 0 2 by 15 plus 0 into 1 1 by 15, 0 into 2 1 by 15, 1 into 0 3 by 15 plus 1 into 1 2 by 15 plus 1 into 2 1 by 15 and so on. So in this fashion you can find out the expected value of xy also. Yes, any question till now? Am I audible?
Yes, sir.
Okay. So,
Yes, sir.
okay, okay. So in the same fashion, for the continuous random variables, you can define the joint probability density function fxy, which is greater than equal to 0. X is between minus infinity, y is between minus infinity and infinity. And instead of summation, you have double integration now, should be 1. Marginal, in the same fashion, using the Bayes theorem, you can find out fxx as integration fxy dy. Similarly, marginal density of y, integrate over x, conditional of x given y is equal to y, you will find out joint over the marginal. Similarly, conditional of y of x given x is joint over marginal of x. So in the same fashion, for the continuous case also you can do. Now let us take this example. The front tire and back tire of the rover. Rover is a small vehicle that can move over rough grounds, often used on the surface of other planets. So front tire and back tires of rover is supposed to be filled to a pressure of 0.4 psi and 0.6 psi. Suppose the actual air pressure in each tire is a random variable, x for the front tire, y for the back tire, and joint probability density function is given by ky, x is between 0 to 1. Now, first of all, find out the value of k. So then find out the marginal density and conditional density. Marginal densities of x and y. Okay, so fxy is ky, x is between 0 less than 1. So now this is x, this is y. X is equal to y is this line. So x is between 0 to 1, y is between 0 to 1. Now y is greater than x. So this is the reason basically we are interested in. Now, because we know that double integration of f x comma y dx dy is 1. So this implies that ky dx dy. So x is varying from here to here. So x is varying from 0 to
Why?
this point y, and to complete this reason we should vary our y from 0 to 1, then this reason will be complete. Okay, so 0 to 1. So therefore this will be k times 0 to 1. Now this will be y square. Okay, so this will be integration over x. Okay, so this will be y will be outside, and integration over x, that will be x which is varying from 0 to y, that will be y square dy. Okay, so therefore this will be k times y cube by 3. So that means 1 by 3.
Hello, sir. Hello, sir. Am
Yes,
I audible? Sir,
yes.
in that, why you have considered x is equal to y in that curve?
H is equal to y. What is h?
X is equal to y. X is equal to
To
this line.
make to make this line.
Okay, okay, okay. Sorry, sorry.
So therefore k is equal to 3. So what is the marginal of x? So that will be integration joint integrating over y. So therefore this will be 3y, k times y, k is 3, y, and y is varying from x to 1.
X to 1.
Yes, x to 1. So x to 1. So therefore this will be y square by 2. So 3 by 2 and 1 minus x square. X is between 0 to 1. This is the marginal of x. What is the marginal of y? Marginal probability mass function. Integration joint integrating over x. So 3y dx. X is varying from, so x is varying from here to here. Kindly mute yourself. I think Chirag previously was. Yeah, Chirag, why are you? Yes, Chirag, why are you unmuting yourself again and again?
Yes, sir, I do so.
You are previously also you are. So kindly mute yourself. Na? When some question is there, then unmute. Okay.
Yes, sir.
Kindly mute. Mute now. You have some question?
No, sir. No, sir.
So why are you unmuting? Kindly mute yourself. Okay, now I am muting. So kindly don't disturb the class. Na? If some question is there, then only you unmute. Okay, so this is 3y dx. So now 3y, so y x is varying from this point to this. That means 0 to y. So this will be 3y into x, which is from 0 to y. So 3y square. Y is from 0 to 1. So in this fashion, you can find out the marginal of x and y, marginal density of x and y. So if you want to find the conditional density of y given x is equal to x, so that will be joint over the marginal of x. Joint is given by ky. Okay, so k we have find it out as 3y upon 3 by 2 1 minus x square. So that will be 2y upon 1 minus x square. So where y is between x to 1. So now let us. So any question till now from any student?
Excuse me, sir.
Yes.
Sir, can we use this conditional distribution to directly find the conditional probability?
No, you have to find out the probability basically. For example, I want to find what is the probability that, let us say that this random if I represent this by, let us say, random variable u, I am representing that y given x is equal to x. So if you want to find out u greater than some, let us say, some 0.5, then you have to use like this 0.5 to infinity to 1 or whatever the point. Okay, so then, or whatever the point is there, to infinity, or in this case 1, then f u du. So in this fashion you can find out. As you know that already discussed that probability density function does not represent probability, but area, this area basically represents the probabilities used to find out the probabilities basically. Is it okay or not?
So, sir, why find conditional distribution?
Because they are used to find out the probabilities, na? That's why, and mean and variance, etc.
Okay, sir, understood.
Because you have the CDF, derivative of CDFs are known as the probability density functions. Okay, so probability density functions basically uh, used to find out the probabilities basically, but as such they doesn't represent any probability. But you can find
Yes, sir,
out
understood.
probabilities using these. Yes. Okay, so x and y are said to be independent if the joint CDF, cumulative distribution function, which is probability x is less than equal to x, y is less than equal to x. Okay, so if this can be represented as probability x is less than equal to small x, which is probability y is less than equal to small y. If this happens, then x and y are said to be independent. If the joint CDF is product of their marginal CDFs, okay, is product of their marginal CDFs, then x and y is said to be independent. So using that, you can easily find out by taking the double derivative that joint probability density function is product of their marginal density functions. And similarly for the discrete case, the joint probability mass function is product of their marginal probability mass functions. Okay, so this is the joint CDF fxy. Okay, so if this joint CDF is product of their marginal CDF, then x and y is said to be independent. From there, we will get these two definitions also in the discrete and continuous case also. So a binary message is transmitted, which is either 0 or 1. Assume that the channel has additive noise and it corrupts the transmission. Let x denote the transmitted message, y denote the received message by the receiver. X and y have joint density function as the message which is transmitted is 0 It is received as 0 with probability 1 by 4. It is transmitted as 0, received as 1 with probability 1 by 4. It is transmitted as 1, received as 0 is 1 by 4. Similarly, transmitted as 1, received as 1 as 1 by 4. So what is the marginal density of x? So marginal is easy to find. So you will sum over y values. So summing there here. So 0, 1 by 2, 1, 1 by 2. Okay. Similarly, marginal density of y. So corresponding to y, you have to sum over x. So corresponding to probability y is equal to 0 is 1 by 2. And similarly, probability y is equal to 1 is 1 by 2. So this is the case. So now whether x and y are independent. So you have to just see the whether px x and y basically 0 and 1. So you can easily see that p00 is 1 by 4, px0 is 1 by 2, py0 is 1 by 2. So 1 by 4 is equal to 1 by 2 into 1 by 2. Similarly, px 0 comma 1 is 1 by 4. So px 0 is 1 by 2, px py 1 is 1 by 2. So this is also 1 by 4 is equal to 1 by 2 into 1 by 2. So whatever case you take in this case, whether p 0 comma 1, 1 comma 0, 0 comma 0, 1 comma 1, in each case this is holding, because this holds for all x and y. So therefore x and y are independent. Now let us see another example. Let us take f xy as 6 x square y. X is between 0 to 1, y is between 0 to 1. So what is the marginal distribution of x? Can anyone find out what is the marginal distribution?
Three. 3x.
X square.
Yes. So this is 6 x square into y square by 2. So that is 1 by 2. So therefore 3x square. X is between 0 to 1. And what is the marginal of y? That is 6 x square y dx. X is between 0 to 1 also. So this is also
2y.
yes. So 6y into x cube by 3. So that is 1 by 3. So therefore this is 2y. So in this case also fxy is equal to fxx fyy. That means the joint is product of their marginals. So therefore x and y are independent. Okay, so in this case also x and y are independent.
Sir,
Yes.
sir, if there is a condition like 0 less than x, less than x, less than y, less than 1. So in such conditions, can we directly say that it won't be independent because the area of region is dependent on both, like 0 less than x,
You
less
have
than
to,
y.
then you have to find out na, that similar kind of case we have discussed just now, that you have to do, you have to plot this area and see.
Yes, sir. So
For example,
in
this
such
type of area is
example,
there. You can find out the marginal and marginal find out and see whether joint is product of their marginals or not.
Yes, sir.
Okay, so you have to do that. Now let us define covariance. So x and y are random variable with means mu x and mu y. That means mean of x is denoted by mu x. That is nothing but expected value of x, and this is expected value of y. Then covariance between x and y is defined as expected value of x minus mu x, y minus mu y. So if we define covariance between x comma y as expected value of x minus mu x, y minus mu y. Okay, so therefore this can be written as expected value of xy minus mu xy minus x mu y plus mu x mu y. Now, because you know that this expectation is over, basically two values are there, x and y are there. So previously expected value of x was there, so one summation was there, x px. But here two values are there, x and y random variables are there, therefore this is xy minus mu x y x mu y plus mu x mu y into the x comma y, the joint. Let me take, if both of them are, if the discrete case I am taking, continuous case same way you can go, instead of summation integration will come. So therefore this will come as double summation xy pxy minus mu x and summing double summation x y. Okay, let me take y here, x here, y pxy minus mu y summation x x summation y pxy plus mu x mu y double summation xy pxy. So this is nothing but the definition of expected value of xy. And can anyone tell what is this value equal to? If I sum the joint probability mass function over x, what I will get?
The marginal
Marginal.
of y.
Yes. So we will get the marginal of y. This will be p by the definition y. So now we have summation y p y. So mu y, that is mu y. Similarly, this will be marginal of x summation x px, that will be mu x plus mu x mu y. Double summation is 1. So summing the joint density over x and y is 1. So therefore one of the value will cancel out. So therefore this is expected value of xy minus mu x mu y. So in this fashion we can find out the covariance between xy as expected value of xy minus mu x mu y. Okay, so in this fashion you can do the proofs basically in the same fashion. So if your x and y are independent, then covariance between x and y is 0. But converse may not be true. So let us show that x and y are, if x and y are independent, then covariance between x comma y is 0. So what is the meaning of independence? That means let us take the discrete case. The joint is a product of their marginal probability mass function that is given. We have to show that covariance is 0. This is to show. Okay, so but covariance xy is nothing but this value also. That means we have to show that expected value of xy is basically mu x mu y, expected value of x, expected value of y. That is the same thing. So let us start from one side. So expected value of xy, this is double summation xy xy pxy. So this for therefore this, but we know that given is this, they are independent. So therefore this is pxx py y, because x and y independent. This is given to us. So therefore this will be summation x x px summation y y py, taking this as common, summation x px. So therefore this is nothing but mean of y. This will come outside. Remaining is inside is this value, which is nothing but mu x, mean of x. So therefore we have shown that expected value of xy is equal to mu of x mu of y. That means covariance xy is 0 if x and y are independent. So therefore we have shown this thing, that if x and y are independent, then covariance xy is 0. For example, you see this. So if x and y are independent here in this example, so this will imply that covariance between x comma y is 0 in this case, because x and y are independent. So I don't have to show anything, because I have proved this, that if x and y are independent, then covariance x comma y is 0. But if x and y are then it may or may not imply that x and y are independent. Okay, so but the converse may not be true. So for example, we take this. Consider x and y having density pxy as this. X is -1, y is -1, value is 0. X is -1, y is 0, is 1/4, and so on. Then what is the marginal density of x? So marginal, you will sum over y, 1/4, -1, 1/4, 0, that is 1/2, 1, 1/4. Marginal density of y is corresponding to -1, value is 1/4, corresponding to 0, value is 1/2, corresponding to 1, value is 1/4. Now you can easily see that px -1 -1, px -1 here is 0, and px -1 is 1/4, and py -1 is 1/4. So therefore they are not equal. So therefore x and y are not independent. X and y are not independent. But covariance xy, so you can easily see that what is the mean of x here? What is the mean of y here? Can anybody tell?
So mean of x is
The
0.
0 0.
Yes. So clearly minus 1 into 1 by 4 plus 0 into 1 by 2 plus 1 into 1 by 4 0, and mean of y is also similarly minus 1 into 1 by 4 plus 0 into 1 by 4 plus 1 into 1 by 4, that is 0. And what is, but we know that this is expected value of xy minus mean of x into mean of y. Okay, so this is expected value of xy minus expected value of x, expected value of y. So expected value of xy, this is double summation xy, xy, pxy. So minus 1 into 0 plus minus 1 into 0 into 1 by 4 plus minus 1 into 0 into 1 by 4 plus 0 into minus 1 into 1 by 4. That will be 0 all. 1 into minus 1 into 0, 1 into 0 into 1 by 4, 1 into 1 plus 1 into 1 into 0. So that is also coming out to be 0. So therefore this value is 0. So covariance xy is 0. Okay, so this is the example where covariance xy is 0, but x and y are not independent. So we may find some examples where converse may not be true. So that example we have given may or may not be true here. Okay, so covariance x and y are independent, then covariance xy is 0, but covariance xy is 0, that may or may not imply that x and y are independent. Now correlation. So what this covariance xy represents? So if we define, because covariance xy is between minus infinity to infinity, okay, so we can divide by sigma x, variance of x, standard deviation of x, because okay, this is under root of sigma square. So that means standard deviation of x under root of variance. So covariance xy divided by sigma x sigma y. So it can be shown that the correlation coefficient is between minus 1 to 1. And when mod of correlation coefficient is 1, if and only y is equal to alpha plus beta x for some real numbers alpha and beta, which is beta is not equal to 0. That means if correlation is coefficient is 1, then x and y are basically lie on a straight line. Okay, so that means there is a positive association between x and y if correlation coefficient is 1. If correlation coefficient is negatively associated, then all the data points between x and y are basically lie in this fashion, and x and y are uncorrelated if covariance xy is 0. Okay, so that is the definition, basically covariance xy is 0. So if correlation coefficient is between 0.5 to 1, then there is a strong association between x and y, positive association. X increases, y also increases. If it between 0 to 0.5, then we can say that weak positive association. At 0, so we can say that x and y are uncorrelated. And similarly, if negative side, minus 0.5 to 0, weak negative association between x and y. And if between minus 1 to minus 0.5, strong negative association between x and y. Okay, so in this fashion, if x and y are independent, then correlation coefficient is 0, but converse may or may not be true. The same example will work. The example which we have just given, the same example will work for this. X and y are independent, then correlation coefficient is 0, but converse may not be true. Okay, so any question till now? So let us stop here. So next time we will start with some these kind of relationship which will be used later. So any question till now?